Thank you for joining the Kent Seminar Series last lecture of the semester. Today we have Professor Paul Kwiat. Dr. Kwiat is the Bardeen Professor of Physics and the Director of the Illinois Quantum Information Science and Technology Center at UIUC. His research interests include advanced quantum communication, optical quantum metrology, and fundamental quantum physics. Dr. Kwiat earned his bachelor's from MIT and his doctorate degree from UC Berkeley. And today he's here to talk to us about how quantum information science has something to do with transportation. And just some housekeeping reminders for everybody. You can use the chat tab to submit your questions. You can raise your hand by clicking on the participants tab and going to raise hand. Professor Kwiat is going to have 40 minutes for his presentation, and then we're going to have a Q&A session. And I'd be glad to help you with the questions if you type them in the chat, or let you know when you can ask your question, unmute yourself and ask your question. So with any further ado, Professor Kwiat.
Thank you. Thanks very much for the invitation. Thanks very much for the invitation to come here. I'm happy to maybe be able to explain just a little bit about some of the things that are going on both on campus and how they and globally actually, and how they might be relevant in rather a different sphere than they've been considered in the area of transportation. So I'm presuming that you can see slides now. Yes, we're all good.
Yes, that is correct.
So let me just get rid of that. So I have a habit of always changing my titles just a little bit. So I'm going to sort of expand this, and not only planes, trains, and automobiles, but other sorts of transportation platforms like drones and satellites. And really, we're in the area now where we're moving beyond science and into engineering for practical applications of some of these things in the quantum engineering space. So just to make the kind of connection with the movie Planes, Trains, and Automobiles, which some of you may not have seen or may not have seen in quite a while, I kind of summarize what the, or let's just say I'll repurpose what this plot line is that we have this hero who's having to struggle with a number of transportation platforms, basically, and various annoying adversaries in an attempt to reach his goal, in this case, to get home. And at the end of this, he sort of discovers a lot of new connections. And so, in some sense, that's the same thing I'm going to discuss here, is trying to hopefully develop new connections between my field, quantum information science and engineering, and the transportation era. And this is definitely a case where you probably don't know a lot of quantum information, and I equally don't know a lot of the transportation difficulties. And so being able to have a conversation about that will, I think, be very helpful. Okay, so this is a quick outline of what I'd like to do. I want to spend just a couple minutes giving you a sense of the landscape, the quantum landscape, both locally and also nationally and globally. I'll talk a little bit about the fundamentals of how quantum information works and why it's potentially helpful. And then I think maybe most interesting will be sort of my list of potential applications in the transportation space. And if there's time, I'll talk a little bit about the specific things that we're working on in my own research group, but that's not really the purpose of this. And so that might get jettisoned depending on the timing. So I think I passed a slide, there we go. So quantum information is this field that came up roughly almost 30 years ago now. And the idea is to use some of the very bizarre features of quantum mechanics that you might have learned about in some class, that I'll talk a little bit about here, to solve some kind of problem in information processing. And that has a whole range of different arenas where that applies, from computation to communication to metrology and sensing. There's a lot of interesting fundamental science underlying all of this. And to make many of these systems work, you need to have better materials. And so there's sort of a new push toward making so-called quantum materials, which are optimized for these sort of applications. So this is not a particularly small effort. So this was from an article in The Economist in 2015. And you could see that at that time, there was about $1.5 billion around the world being devoted to this. And this is a more up-to-date estimate just from this year, where now there's an estimated 2.5 billion. Now, I know for you people in transportation, 2.5 billion probably doesn't seem like very much if you compare to, the infrastructure, even just in the United States. So that's in some ways a very small amount. But I'd like to point out that this is a 15-fold increase in just a few years. And things are continuing, I think, to ramp up. And so it's definitely a case where we could say we're in the midst of the quantum information revolution, I guess. And just more sort of locally, not in a global sense, but in the United States, the US has been funding quantum information research for a couple decades, three decades, I guess, through the National Science Foundation and some other efforts. But there's really been a rather large boost in that as of the end of 2018, when the National Quantum Initiative was signed. And there are a number of now government reports that you can read out of the White House. There's now a National Quantum Coordination Office, things highlighting how quantum information science is going to be important for national security, economic applications, and things like that. And there's a growing focus also on networking. And this networking is the case where there's certainly likely to be implications for the transportation space. And so I called out just one of these. We don't have to read the whole thing, but we can, just looking at the kind of the red highlighted text. Again, this is just from basically over a year ago, where there's now a push to try to pioneer platforms that will link together different quantum devices. And those will lead to applications in security, sensing, and computing. There's still a lot of fundamental science and engineering technologies that need to be developed for this. But those will then lead to impact in the commercial sector, scientific sector, health, national security, and the transportation was not specifically called out, but I feel like it touches on all of those different aspects. And so I definitely think that there's a connection. And as part of the National Quantum Initiative, there were set up already 8 kind of large centers, 3 National Science Foundation centers and 5 Department of Energy centers. And in fact, we're at UIUC associated with 3 of the 8, as it turns out. So it was about 2.5 years ago that IQUIST, Illinois Quantum Information Science and Technology Center, was stood up by the campus. And we currently consist of 40 faculty members across 9 departments, and broken into a number of different areas in computing and in communication, quantum materials, and metrology and sensing. Okay, so the point of all that is that we have people from a number of different departments, and the idea is to try to make connections in areas that we don't already have them. And so that's one of the reasons that I'm very happy to be here and sort of brainstorm with you, as it were, what other areas this might be relevant in. We're also a member of the Chicago Quantum Exchange, and which is, what will I say, an organization that consists of us and Chicago, University of Chicago, Fermilab, and Argonne National Lab, as well as Northwestern, and it's not showing on this map, but also University of Wisconsin. And there's also been now a promise from the state of Illinois through the Rebuild Illinois Act to invest $200 million in supporting the Chicago Quantum Exchange, and 100 million of that is basically to support UIUC's efforts in that. And just this is my last sort of history slide or background slide, which is that we've, as I indicated, we're actually strongly involved in several of these large centers. Brian DeMarco leads this National Science Foundation Center on Hybrid Quantum Architectures and Networking. And we're one of the main players in QNext, which is the Argonne National Lab-led DOE Center. We also have a participant in the Fermilab led DOE center, and we've also recently got DOE EFRC, Energy Frontier Research Center, to study quantum sensing and quantum materials. So there's really a lot of activity that's going on here, and hopefully we can expand that further. Okay, so maybe on to more fun things. So quantum mechanics 101. I'm going to assume, so this is a kind of a tricky audience that I'm not used to talking to. I'm used to talking to either people who know quantum physics pretty well, or broader public audiences who don't necessarily know any science or anything technical. And so you're kind of in an unusual sweet spot where you're probably technically savvy, but not necessarily quantum mechanically savvy. So I'll try to put this at, hit that audience as best as I can. So we can understand quantum information sort of easiest by comparing it to classical information. So classical information, of course, is based on bits, so states that can be zeros or ones. And in the quantum case, we also can have states that can be 0 or 1. But the thing is, we can also have arbitrary superpositions or arbitrary combinations of zeros and ones at the same time. And maybe to have that not be so abstract, we could just think of a couple different examples of that. So one example, I have a prop here. So one example I could think about, for example, the polarization of a photon. And if it's a horizontally polarized photon, I could call it a 0. And if it's a vertically polarized photon, I could call it a 1. And I could also imagine, for example, having a diagonally polarized photon that would be a 0 plus 1, or an anti-diagonal would be 0 minus 1. And if instead I had circularly polarized light, that would be 0 plus I1. So you can see in this case that the state, the way to describe these states, instead of just being a binary choice, we actually describe them as living somewhere on the surface of the sphere. So it's a much more complicated, rich space in which to do things. And if you think about for example, with classical information processing, with a classical bit, kind of the only two things you can do to it is you either leave it alone or you flip it. That's really all you can do. Whereas in the quantum case, you can take this sphere and you can rotate about any axis by any angle. So it's a much richer structure. The other thing that's quite different about quantum information than classical information is that you cannot copy quantum information. So it's so-called unclonable. And that's going to be important for some of the security applications like quantum cryptography, the fact that it's not possible to make a copy of an unknown quantum state. Okay, so this is kind of, qubits or quantum bits are the sort of fundamental unit that most of the things we deal with work on. The other thing that's kind of fundamentally important for quantum information and for some of the things I'm talking about is this phenomenon of entanglement. Entanglement describes the fact that if you have two different quantum states, you sort of have two different options. They're either such that they're completely independent of each other. So the total quantum system, you can write just as the quantum system of one and the quantum system of the other one, and that's it, they're independent. But there are also states where that's not possible to do, so-called entangled states. This is an example shown here. And in that case, if you ask about either subsystem, neither subsystem in this case, for example, is a 0 or a 1. So if you just look at subsystem 1, the one on the left, it's not a 0, it's not a 1, it's really 0 and 1 at the same time. But if you were to measure particle 1 and find out that it's a 0, then you could say with certainty that if someone measured particle 2, they would also find that it was a 0. So it's equally likely whether you find out whether it's 0 or 1, equally likely whether the other person finds out it's 0 or 1, but you're always guaranteed to get the same answer. So there's a sort of non-local characteristic to the information. So maybe the best example I can think of to describe it, kind of a concrete example, is just imagine having two coins. Each of them is completely random what result that they'll come up with, and yet they're always guaranteed to come up with the exact same result. And it turns out that that can be quite useful. So if I ask why that might be important for example, for quantum computing, if we imagine that we had classical information, say a 3-bit register, then each of those elements of the register can be either a 0 or a 1. And so I'm going to get a total of 2 times 2 times 2, or 8 possibilities. So I can store one of the 8 numbers from 0 to 7. And if I have the quantum case instead, if I can make each of these registers into this superposition where it's a 0 and 1 at the same time, then I simultaneously can have all 8 of those numbers in my quantum computer at the same time. And with only 3 registers, that's maybe not that amazing. But if you imagine that I had, say, 300 registers instead, a 300 qubit register, that would simultaneously be able to encode and operate on 2 to the 300 numbers. And 2 to the 300 is roughly 10 to the 90. And that's actually more than the number of particles in the universe, in the known universe. So if you count all the electrons, you'll run out of electrons before you get to 10 to the 90. So there's this incredible parallelism, if you want. But quantum computers are only going to be useful at solving problems where there's a very small number of answers in kind of a large space. So although it's true you could use a quantum computer to simultaneously calculate the inverse hyperbolic tangent on all 2 to the 300 numbers simultaneously, you could do it all in one step. If you made a measurement at the end, you'd only get out one answer. And so that's not very, and it would be random which one you got out. So instead you need problems where there's sort of only one answer that you care about. And so there's some subset of problems that quantum computers are good at. So one of them, and the thing that kind of started the field, was being able to crack codes, basically being able to factor large numbers into their prime constituents much faster than any classical algorithm could. And so this is just showing, for example, how long it would take to factor a 129-digit number, which is a length that was typically used in the RSA encryption code. And on a typical PC, it might take a few months. On our UIUC supercomputer, Blue Waters, it might take a second. And on a quantum computer running at a gigahertz, it might take 10 seconds. And you say, that doesn't sound like a very good deal because we can already do it faster on Blue Waters. That's true. So let's instead, let's just make it roughly twice as long, twice as many digits. And now my PCs are going to take hundreds of thousands of years. Blue Waters, takes a couple weeks, and my quantum computer goes up to 1.5 minutes. And if I make it even just a little bit longer, now Blue Waters will take 20 million years, and my quantum computer only takes a few minutes in order to get the answers. So there's definitely an exponential enhancement in the speed of being able to crack one of these codes, basically. Another thing that's maybe more interesting to us and maybe more useful in the computation sector would be the quantum computers are now known to be good at optimization or combinatoric optimization, where the goal is you have some resources and you want to figure out what's the best way to allocate them in order to solve some problem. So just practical examples of that might be, how to distribute protective, masks and things like that, PPE or vaccines, or if you're Amazon, how should you optimally try to deliver packages so you use as little gas as possible, or if you're trying to have a lot of information flowing around the internet, what would be the best way to route that? So quantum compute, that's again a type of problem where there's a lot of possible variables, but there's kind of only one right answer, or maybe a small set of equivalently correct or good enough answers. And quantum computers are known to be able to solve such things. And then the other application is in the area of basically solving quantum mechanics problems. So if you think about a quantum computer as this large collection of quantum systems that are interacting with each other in exactly the same way that any classical computer can simulate any other classical computer, that's one of the kind of fundamental tenets in computer science. A quantum computer is therefore able to simulate any other quantum system. And essentially, of course, any small or large molecular system is just a complicated quantum system where you're trying to figure out where all the electrons will go. They're all repelling each other, but they're all attracted to the nuclei, and they can't quite overlap because of the so-called exclusion principle. So this is a problem which cannot be solved using a classical computer. It rapidly becomes far too complex. And so the idea is to use quantum computers to be able to do simulations, to be able to discover new materials, model how complicated proteins behave. That could be important for biological applications, drug research, and I'll give some other examples in a little bit. So just in case you haven't been, following the news on this sort of thing, where are we at present? So we're actually in what is known as the NISQ, noisy intermediate scale quantum computing era. So I just gave a bunch of examples, and none of our computers are really good enough to do those kinds of things at the moment. So at the moment, we're sort of at the scale of 50 to 100 qubits. This was from a couple of years ago. Google, who has a large quantum computing effort, managed to get their computer, their state-of-the-art computer at the time, with 53 qubits, as shown here, 53 qubits in order to solve a problem. And it's not a problem that anyone would really care about, but anyway, they solved this problem that a classical computer, they estimated would take 10,000 years. Then IBM came back and said, no, actually, if you're more clever about how you do your classical computation, you could do it in a couple days instead of in 10,000 years. But nevertheless, this was the first demonstration that had been done of so-called quantum supremacy, where the quantum computer is able to do something faster than any classical computer could. Not anything useful, but anyway, something faster. So we're in this regime now where the computers that people don't have lots of qubits. The fidelities are pretty good, but not really quite good enough. The number of gates are pretty high, but like nowhere near good enough to do these large-scale molecular simulations. So scaling up is challenging, and it's likely that we will need hybrid approaches that are combining different sorts of physical platforms. Okay, on the communication side, I'll just give a couple examples of that. One of them is using this entanglement that I talked about in order to do encryption. And so we can make a source of entangled photon pairs, and I send one off to one person called Alice, one to the other person called Bob. And in this particular case, they're entangled in polarization. So either both photons are horizontal or both are vertical. It turns out if you also represent in the diagonal basis, you'll find out that the photons always look the same, actually also in the diagonal basis. So as long as they're measured the same way, you're guaranteed to get the same answer. And the way that you can use this for encryption then is that you send one photon to each person, and they each, for every photon that comes to them, they randomly decide to either measure them and ask, are they horizontally or vertically polarized? That's one type of measurement you can make. Or are they diagonally or anti-diagonalized, diagonally polarized? That's a different type of measurement. Turns out you can only make one of these types of measurements per photon. Once you make that measurement, then you're done. You can't make a second measurement. And so the people in this protocol, they randomly measure each photon that comes to them in one of the two bases, and then they have a public discussion in which they announce what bases they used for every given photon, but not what the results were. If they use different bases, they just throw things away, and that'll happen about half the time. But if they use the same basis, they'll keep their results, because if they use the same basis, they get perfectly correlated results. That's the meaning of the entangled state, that if Alice saw horizontal, Bob saw horizontal, or if Alice saw -45, then Bob saw -45. And then they can simply agree to assign horizontal and vertical polarization to, horizontal and diagonal to a 0, vertical and -45 to a 1. And the consequence of this is now they have this shared key. They have a random string of numbers, just zeros and ones, that they each know, and it's the same secret key. And then the next piece that's critical about this is no one else knows what that key is. And so that's why it's called a secret key, of course. And then once they have that string of random zeros and ones, then they can use that to do perfectly secure encryption. So provably secure encryption. That's not hackable in any way. Well, it's basically provably non-hackable. So entanglement has some advantages. It turns out you don't need to use entanglement to do quantum cryptography. You can do it just sending single photons, but entanglement has some benefits. And one of them, it's the only one I'm going to mention here, is that, in fact, you don't have to trust any of your equipment. The source could be sold by some intermediate eavesdropper. Right, I should say one thing about why is this whole thing secure? It's secure because an eavesdropper cannot copy the quantum signal going from the source to either of the two people, because that would violate this thing called the no cloning theorem. I said you can't copy quantum states. So the eavesdropper can't copy it. The best she can do is make a measurement, And because Alice and Bob are randomly deciding how to measure each of these, if there's an eavesdropper in the middle, she doesn't know the right way to measure it. And so she'll measure it sort of the wrong way half of the time. And that will introduce errors. And Alice and Bob can detect those errors. And then they know that there's been someone eavesdropping on their signal. So you get you can always detect the presence of an eavesdropper in this sort of scenario. So it's possible to connect stations that don't even see each other directly. I think I don't want to go through that in detail other than to say that if you have some trusted node in the middle, that you can then share a secret between any two people who could see that node, for example, a satellite. Or in fact, if you have entanglement on the satellite and you're distributing, say, entangled photons down to Alice and to Bob, then you don't even have to trust the satellite. As I was just saying, you can generate this secure key and use that. And in fact, just 5 years ago now, there's a quite important result where a Chinese experiment, the Mischius satellite, demonstrated a number of protocols, quantum communication protocols from Earth to space. So they did this quantum key distribution. They distributed pairs of entanglement like I just talked about. And they also did a version of quantum teleportation, which I could talk about later if people are interested. As the last example of quantum communication, I'll give this other sort of relevant or potentially relevant case of position verification. So you could imagine that you want to know where a particular person is, particular node is. You want that person to be able to verify that they are where they say they are, because maybe they're trying to cheat you and they're saying that they're at a different location than they actually are. And so one way that you could do that is shown here. You have a sort of a simple 3-node network. And you've got the two people who are verifiers. They're trying to verify that Alice is where she says that she's at that particular location. This is what the actual protocol would look like in terms of sending, in this case, it would be, say, horizontal, vertical, or diagonal or anti-diagonal photons from the verifiers to the receiver. But I don't really, the details aren't really important, except to say that there are some quantum questions that Alice has to answer in a short time. And it's important, in a sense, this is sort of combining quantum mechanics and relativity, the fact that it takes a finite amount of time for the signals to travel. They can only travel at the speed of light or slower. And so in order for Alice to be able to return an answer quickly enough, she really has to be in the location where she has claimed to be. If in fact that she's further away, if she's sitting down here, for example, then it would take her longer to return the answer to the two verifiers. And then you would know that she wasn't sitting where she said she was sitting. And this is a protocol that actually doesn't require entanglement, so it's a little bit easier to implement. In the area of sensing and metrology, there are a number of different benefits in the quantum space. So one is that if you are preparing these correlated photons, so you have these photon pairs, or even if you just have a source where you know that it's emitting exactly one photon, that means you can be quite robust against noise because you can just detect, you know exactly when that photon is supposed to arrive. And maybe also some characteristics about that photon, so you can use that to suppress background noise in some way. It turns out that if you have entangled sensors, n entangled sensors, then you can get an enhancement in the precision of measurements made by those sensors, an enhancement that grows as the square root of n. And as the last example that I've written here, you can use interference to amplify some kind of a weak signal. And it says here that's helpful if this thing you're looking at is not quantum noise limited. So let me just give a simple example of that. Let's say you have a laser pointer and you want to see exactly which way it's pointing. And so what you could say, well, I'll just look at a faraway wall and I'll just see how far it's translated on the wall. And if I know the distance, then I can take the inverse tangent and I can get the angle. So I can get the angle of pointing. But let's say that as you know, laser beams, they diverge a little bit. They don't stay perfectly focused, they diverge somewhat. So let's say that the angle that the thing's being tilted is much less than the divergence angle, so that on the wall, the spot is just moving a small fraction of the overall size of the spot. That in general could be pretty hard to see. And in particular, if, for example, if the thing you're measuring with, if a wall were moving, that could make it very, very difficult. And so by using these sort of quantum interference techniques, you can effectively amplify the angle by, let's say, a factor of 1,000. So instead of on the wall moving only 10 nanometers on the wall, which if the wall itself is vibrating, on the scale of a micron, you'd never be able to see a 10 nanometer, or it would be very difficult to see a 10 nanometer shift against a background that's moving 1 micron, 100 times that. In this case, if you were to amplify the signal by a factor of 1,000, then you have a signal that was 10 microns over a 1 micron background. So it'd be a lot easier to see. I'll just say a brief word about this. So this is a way of using pairs of photons to get very fast, very precise, I should say, timing resolution measurements. So basically, you send 2 photons, one goes one way, one goes the other way, and we're going to try and measure if there's a delay, a relative delay between the 2 paths. And we'd like to measure that really pretty sensitively. And in fact, with this sort of a scheme, it turns out you can measure that at the attosecond level, maybe 10 attoseconds or something like that. So it's a very, very precise measurement. And you can do measurements like this in other ways. So you can do measurements like this, for example, this is in a sense what, if you want to think about it, what a LiDAR does. So if we look at the signal that's bouncing off of something and then coming back, that's how we can detect, for example, how far away that object is. It turns out, though, that that's going to be, LiDAR will be susceptible to background noise and also to loss in the signal. You can also do something where you make a big classical interferometer, and that can also have very good sensitivity. But it's also sensitive to noise and to loss in one arm. And it turns out that this particular method, turns out, is immune to loss, relatively immune to loss, and also to background noise, and also to dispersion, it turns out. Quantum radar is, this is a fairly recent paper, but it just highlights this fact that if you have n entangled systems, that you can get a reduction in uncertainty in some measurement by a factor of square root of n, which again could be useful for some applications. Another one, something that we're working on along with some other collaborators, is trying to make basically quantum telescopes or quantum connected telescopes. So the resolution, the pointing resolution, the angular resolution of a telescope depends on how big it is. The bigger the telescope, the better the resolution is. But you're limited, of course, in how big you can make a telescope, because you can't make a telescope that's, say, 1,000 kilometers on a side, because, for example, if you made it out of glass, there's not enough glass in the whole planet to make a lens that would be that big. So what you can do in the radio is you can break the telescope up into smaller telescopes, as shown here, an array of radio telescopes. And the signal comes into each of them, and you can combine those signals so-called coherently so that they act like one big telescope. And that works fine in the radio, and in principle would work fine in the optical domain, except that you have to somehow bring the signal from one telescope to the other one. And if they're separated by more than, let's say, a kilometer, you have too much loss, and that ends up being, you basically can't do it very well. And so the idea is that you might be able to use quantum communication to basically link up these 2 telescopes. And if you could do that, so this type of telescope is known as a very long baseline interferometer, VLBI, very long baseline interferometer. And with standard things that astronomers currently use, their separation of their telescopes is maybe 100 meters, and their wavelength is maybe 1 micron. And it turns out the angular resolution is just the wavelength over that size of the separation of the telescopes. So they get a resolution of maybe 10 to the minus 8 radians. Whereas if we could instead do a quantum version of this, then we could have these sensors that would be separated by a much larger distance and would get many orders of magnitude enhancement in the resolution of that sort of a sensing system. Okay, so quantum networks are ways of hooking together different quantum nodes. And those quantum nodes could have just a few qubits or a whole quantum computer. We send signals back and forth with photons, and the idea is to have these nodes all entangled with each other. And the reason that you might care, I've already talked about doing secure communication and the fact that we can detect an eavesdropper. I've also talked about the fact that we can make better measurements by having these distributed quantum sensors, for example, for telescopes. And the other one I didn't talk so much about is actually connecting together quantum computers, where if you have several quantum computers acting together as one big quantum computer, then they can solve problems that would be kind of impossible to solve otherwise. And in fact, that may be the only feasible way to make a very large quantum computer. So just as sort of one theoretical example of this, you might have 4 different users and they want to compute some overall function depending on parameters that each of them have. For example, who has the most money? But none of them wants to reveal exactly to anyone how much money they actually have. And so the idea with this sort of distributed protocol is that you'd be able to calculate this so everyone would believe the answer, and yet no one would have to reveal what their actual to any other particular person, what their actual money was. So you can imagine lots of other potential applications or protocols like that. So we are, in terms of networking, we are trying to set up such a network here on campus, QuickNet, involving several of our labs from researchers in IQuist joined together. And then from there going to NCSA, and NCSA has a direct fiber link that leads up through Rantoul, through KC, and eventually up to Chicago. And so we're trying to make a quantum link from here up to Chicago. And one of the key relevant pieces of this is that I know that in Rantoul, there's planned now the IACT Transportation Autonomous Vehicle Testing Center. And so it'd be really interesting to try to couple that into a quantum network, basically, to have both a wired quantum network with optical fibers, as well as a wireless connection to that. Okay, so in my last couple minutes, let me just highlight some potential applications of why you might care about this. And let me just stress, a lot of these are, they're speculative, and they absolutely might require technologies that are not yet completely developed. But in the quantum computing space, for example, in optimization, talked about traffic routing as an example, or you have a bunch of packages and you want to figure out what's the optimal order in which to deliver them to save on gas. Or maybe inside of a transport ship where you have thousands and thousands of these crates that are going to different destinations. The question is, what's the optimal order in which they should be packed inside of the thing so that when you're unloading them, you can do that most efficiently. Or if you imagine a bunch of vehicles that are moving around, communicating and sending communication to each other, wireless communication, there's a lot of packet transfer that has to happen there. What's the most efficient way for that to happen? And I just wanted to say, unless you think that this is too pie in the sky, that there's already been some auto companies that have been working with preliminary quantum computers to start understanding how they would apply those to problems like traffic flow, for example. In the area of doing quantum simulation, where you can do better, hopefully design better materials, that might help making more efficient batteries or more efficient solar cells. And obviously those would be important for the transportation industry, making potentially lighter and stronger materials. And I just added this last one. This is just a crazy idea I had, but maybe you could come up with some sort of relatively cheap road surface that would enable you to simultaneously be collecting energy from the sun. So it would be a power source as well as a, kind of just sitting out there. Okay. In the quantum sensing regime, I've already mentioned sort of LiDAR applications and radar applications and quantum telescopy. Actually, I guess I've mentioned all of these. Quantum position verification. So you could imagine that you have a package that's being shipped and you want to verify where that is at some time. Or maybe you want to verify the whole trajectory that package or that truck or whatever the platform that we're considering would take. And then finally, in the communication and security lane, I talked about the fact that we have the possibility of having security against any sort of undetected eavesdropper or any sort of security against undetected tampering. So we can use that to do encryption. If two people start out with a small bit of secure key that they trust, so for example, when a vehicle leaves the home station, it has a small amount of secure key that it trusts with that, then using these quantum encryption techniques, you can do secure authentication, and you can just keep whatever that initial amount of key was, you can keep regenerating it in a completely secure way. And another potential application you could imagine like a quantum secured tollway or something like that. And then finally, in the communication in sense of doing like a distributed quantum sensing, you could imagine that many vehicles are talking to each other by wireless, and that could start to get to be a pretty electromagnetically noisy environment, particularly if you have a traffic jam and you've got a lot of different vehicles coming around. So there's a question, can we use quantum information methods in order to help sort of sort that out and to have a clearer signal. So I think I'm going to take just one more minute, just not to go into any large details, but just to say that one of the things that we've been working on is trying to do portable, sort of reconfigurable quantum communication, both from drones, and also I have a project trying to develop satellite to Earth quantum communication. And there are a number of reasons why you might want to do that. So maybe you can't, from some platforms, you can't have a direct fiber link, like between ships, for example, and even just going through normal free space, you're limited because the Earth has curvature. So it can be helpful to go to higher altitudes, for example, to be able to get better communication. And in fact, if you're communicating with a satellite, also being able to go up in altitude really reduces the effects of turbulence, and so can improve signals really quite dramatically. And so there's a lot of challenges associated with getting very low swap systems there. I just want to say at the end of that you have then the possibility of reconfigurable networks, which can talk to each other, which can hook into fiber networks, potentially could hook into the this IACT autonomous vehicle testbed, which would be really interesting. And the eventual goal is to have many different sorts of systems that are in contact with each other. I've shown here sort of all the flying ones, well, and stationary ones, but one certainly could imagine also hooking up with various other types of vehicles, other trucks, and delivery systems. So just going to end with a summary here. Hopefully I've given you a sense that there's fundamentally new ways of processing information, and that these quantum technologies could be quite helpful in a number of different arenas in computing, sensing, and communication. And we're now moving toward reconfigurable platforms. And in terms of where do we end up, where do we go from here? I'll close just with another movie reference of, was it Toy Story, I guess, to infinity and beyond. And I'm happy to have a discussion now.
Thank you, Dr. Kwiat, for the presentation. I enjoyed it a lot and found it really informative. We have several questions in the line. First one is Anjali. So Anjali, if you want to unmute yourself, go ahead.
Thank you, Javi. Thank you, Professor Kwiat. Really interesting presentation. Couple of questions. Is the communication one-to-one, or would, for instance, with an autonomous vehicle, utilize the same quantum channel to talk to many other vehicles surrounding it? Like how do you handle right? Is the communication security one-to-one, or could it be parsed to many?
Yeah, so in general, you don't do broadcasting because, for example, I have an entangled pair and then that's shared between the two people, which is in some sense what makes it secure. But you could imagine instead doing routing of that quantum signal. And there's also a way of doing, let's call it, just gonna share my screen for a second. So this is meant to be an entangled source. This is an entangled source. And it turns out that if you combine these two and you make a particular measurement on them, you can cause these two outer ones to be entangled. This is a version, kind of a souped up version of, you might have heard of quantum teleportation. This is called entanglement swapping. The reason that that's relevant is you can imagine having a central storage house which has quantum links with a bunch of different nodes. And then you can decide after the fact, then, oh, I'm going to connect these two nodes, and then those two people will be entangled with each other. Or I'll connect these two nodes, and then these two people will have shared entanglement that they could potentially use.
Okay, and then a follow-up question, what are potential interferences to such communication?
Can you repeat the question?
What could be a potential interference to any type of quantum communication?
Okay, I'm gonna answer two questions, one of which you asked and one of which you kind of almost asked. So the first one is, what causes it not to work? I think that's more or less what you're asking. So we have to be able to detect a single photon or an entangled photon, for example. And we have to do that in the presence potentially of a lot of background. Now that can be okay because, for example, we might know to within a fraction of a nanosecond when that photon is coming. And we might know to within a very good range what the wavelength of that is. And maybe we know exactly where it's coming from. So in principle, we can exclude a lot of background by using that sort of filtering. The next issue is loss, though. So if the photon gets lost, then it doesn't make it to you. And the way that you deal with that classically, for example, like with classical communication in an optical fiber, there's loss in an optical fiber, but you just send an optical pulse that has, say, 1 million photons in it. And if you happen to lose 90% of them, you still have 100,000 photons that got through. In the quantum case, you really have to do things one photon at a time. And if it's lost, then it's lost. It doesn't necessarily hurt your security in terms of these like quantum cryptography protocols, but it does suppress the rate a lot. So loss is definitely an issue, and denial of service in that sense is pretty easy, in the sense that if someone cuts the fiber, if you only have one link, then if someone cuts the fiber, then you don't get the channel. But of course, that's also true with classical communication, right? If you only had one fiber link that was connecting you and I, for example, at the moment, and someone cuts that, we wouldn't have our communication, except that that's not how the network is set up. Because it's a network, if there is a problem in one link or something's going slower in one link, then we can reroute around to a different way. So there are ways of dealing with that. And those would be the same techniques you would use in the quantum case that you do in the classical case. Let me just say that we're really at the early stages of having any kind of quantum networks at the moment. It's early days.
Got it, thank you.
Other questions?
Yes, I was curious to know more about the case of the quantum teleportation. Could you go back to it and explain it to us?
Sure. Let's say that these two guys are entangled. And I'm going to say that they're in this, I'm going to tell you how they're entangled. They're in this particular state, 0, 1, minus 1, 0. Or in terms of, for example, photon polarization, which is kind of what I deal with as a living. I'll do it that way. So they have perpendicular polarizations. And then I have this unknown state that comes in, which has some arbitrarily polarized state, for example. I don't know what it is. And I'm going to make a particular measurement on these two photons, and it's going to have one of 4 possible outcomes. But for one of those outcomes, what I have determined is that these two photons themselves had this same sort of relationship, that they had opposite polarizations. Now, I don't know what those polarizations were, but I know that they're opposite. And if you think about that, if photon 1 and 2 were opposite, were orthogonal to each other, and we already know that photon 2 and 3 were orthogonal, that was by definition of the entanglement that they had. Well, if 2 and 3 are perpendicular and 1 and 2 are perpendicular, then that means 1 must be the same as 3. So in this particular case, if you get that particular outcome, then in fact, this initial state that you had coming in, this unknown state, is now teleported over here. You've converted this photon into an exact, I don't want to say a copy, because this one on the left is now gone by virtue of having made that measurement. And the person over here doesn't know what state 1 was, but by virtue of doing this protocol, state 1 has now been transferred or teleported over to this other state. And if it turns out that 1 was entangled itself already to photon 4, well, now this photon over here, which was originally called 3, photon 3 and photon 4 are now entangled with each other, even though they've never talked. And this is the essential ingredient for making any kind of a large-scale quantum network, for linking together different channels. Does that make sense?
Yeah, in general terms, it does make sense. Thank you.
I'm sorry, say again?
In general terms, it does make sense. It does make sense. Thank you.
Yeah, I mean, obviously I'm giving an extremely high level overview, so I'm not expecting you to, I'm not going to ask a quiz for you to go calculate something based on what I said.
Thank you, because I would be in trouble. But I do understand the overview picture. Thank you. Okay, so if anybody else has questions, you can raise your hand or share it in the chat. All right, we have one from Michael Henny. Michael, if you would like to unmute yourself and ask the question, that would be great. If not, I can read it for you. It says, might photosynthetic asphalt also sequester carbon dioxide and produce oxygen? Perhaps it could fill its own potholes.
Great. Yeah, I have no idea. So this was an idea I just happened to come up with this morning as I was just thinking about what kind of new materials, if you could make any kind of material at all for transportation, what would you want? And you all will have a much better sense of, you'll have 12 ideas that will all be better than anything I would possibly come up with, because you're in the sector, so you know what the limits are. And as long as you don't come up with something that's physically forbidden, in principle, a quantum computer would be something that would potentially be able to help figure out, can you make such a thing, and how would you make it, and how might you make it efficiently? Okay, we're probably 20 or 30 years off before we'd be able to have a quantum computer that could do that sort of simulation. But I guess it's coming.
Well, I think the funny thing is, it's not what you came up with is very realistic. It's one of the research topics we are dealing with. How to render asphalt pavements have properties that enable harnessing of solar energy. So it is something we are working on right now as we speak.
Well, then it was a brilliant idea that I had.
Exactly.
If there is no other questions, Paul, I truly thank you so much. And I think the collaboration that we're going to be having soon, it's going to be very helpful. Actually, Paul, he's leading a project now to see how the quantum going to be implemented as we are developing the I-Act during the design period. So thank you so much, Paul. Well, I don't know if you want to comment on that.
Sure, I'd love to comment on it. I mean, I mentioned a little bit in the talk that we're doing things with drones and autonomous vehicles, and now we're like to try and also connect with not just drones, but trucks, which will probably be a lot easier than drones, I'm hoping, and also stationary platforms. And so we could start exploring the space about using, in my case, I'm a communication person, so that's kind of what I'm most interested in. I wanted to give you a broader overview of where quantum information might be helpful to you in terms of metrology and in terms of computing, even if that's not specifically what I'm working on. I guess that kind of the general thing I would say is just a plea. So I'm at many workshops every year now, for example, with, let's say, the Air Force. And the Air Force wants to know why they're convinced quantum information is going to be good for them. And that's probably true in some regard. But the thing that makes it difficult is that they don't really know what quantum information can do. And so they're trying to come up to speed on that. But the kind of maybe the equal problem is that the people in quantum information don't really know what the problems that the Air Force is really dealing with. And they're often not willing to tell us what the real problems are. And they're not willing to tell us what their current solutions are because everything is classified. So, you guys aren't under those same kind of restrictions for the most part. And so to the extent that we can start having a dialogue between, people in my camp, people in IQuest, and people in your camp, and just kind of brainstorming, just so we start to have an understanding, what are the things that you can't easily solve? And we can start trying to think, are these things that somehow quantum information now or, in 10 or 15 years might be useful to? That's really what needs to happen now. In the transportation sector, in the medical sector, in all of these other sectors, as quantum computing is coming online, I think the analogy that people always give is the cell phone, right? When the cell phone was invented, or what was first thought of, the application was just, I want to be able to talk to someone, but I want to be able to walk across the street when I'm doing it and not have to be tethered to my, to the wall outlet. But of course, that's not what cell phones are now. Of course, people have conversations with them, but there's so many more applications. And the thing that is important is that as part of the capability to become known, it's the people who have needs of those various different capabilities are then bringing them to the attention of the people who make cell phone apps and things like that. So to the extent that we can have a conversation between us more on, what are the capabilities that quantum can bring and what are the needs in the transportation sector, we'll identify a lot of these. This is a relatively new area, I would say. Quantum has just started making its making its appearance in the financial space, where a number of banks and financial institutions, JP Morgan Chase, for example, now has a quantum effort. And they're trying to come up to speed and trying to understand how they can use quantum for securing transactions, for example, or maybe doing faster optimizations in one way or another. So similarly, if we can start having the transportation sector starting to look at this, we'll start to uncover things in a way which is, I guess I would say, ahead of the curve. Okay, that's my pitch.
Well, thank you, Professor Kwiat. Thanks everybody for joining us today and for joining us during this fall semester in the Kent Seminar lecture. We'll see you in the next version of the Kent Seminar.
Thank you very much. I put my email in the chat box. If anyone has any questions or comments, please feel free to reach out to me.